Okay, so how are we going to use these balanced chemical equations? Well, they can be used to predict how much product will form from a given amount of reactant. So we use balanced chemical equations whenever we cook. So if we know that the recipe to make 8 pancakes is taking 1 cup of pancake mix, 3/4 cup of milk, and 1 egg, I get 8 pancakes out. But let's say I wanted to make more pancakes for me and my friends. Well, I say, how many pancakes should I make total? 24 total, great. How many eggs would I need to make sure I have in order to make that amount of pancakes? Well, I would need 3 eggs because 1 egg is for 8 pancakes, so 24 pancakes would require 3 eggs. So we see how this balanced chemical equation or balanced cooking reaction, okay, can be used as a conversion factor. So I'm putting pancakes on the bottom so my units cancel, pancake as a unit, and I'm left with units of eggs in order to determine how many eggs I need to make 24 pancakes. Okay, so we're going to use balanced chemical equations in the same way. So let's look at the reaction of a combination to make CO2. So we have 2 moles of carbon monoxide combining with 1 mole of CO2 to produce 2 moles. So we have 2 moles of carbon monoxide combining with 1 mole of oxygen gas to produce 2 moles of CO2. 2 moles of carbon monoxide is stoichiometrically equivalent to 2 moles of CO2. So however much carbon monoxide I use, I'm going to get out the same amount in terms of moles of CO2 because they are equivalent to each other. So let's look at an example of that. Consider the complete reaction of 3.82 moles of carbon monoxide to form carbon dioxide. Let's calculate the number of moles of carbon dioxide produced. Well, if I start with 3.82 moles of carbon monoxide, I can use the ratio of my coefficients here to convert between CO and CO2. So, because 2 moles of CO is equal to 2 moles of CO2, that's our equivalency that we are going to use to convert from moles of CO to moles of CO2. So we get out that 3.82 moles of carbon monoxide creates 3.82 moles of carbon dioxide because they are in equal stoichiometric quantities. My next question is, how much oxygen was needed to complete the reaction? Well, if we set it up the same way, 3.82 moles of CO, my equivalency now is 2 to 1. So 2 moles of CO is equal to 1 mole of oxygen gas. So we can use that equivalency as another conversion factor. So we put 2 moles of CO and 1 mole of oxygen on the top. That allows us to cancel out moles of CO, and I'm left with moles of O2, and I simply take 3.82 moles and divide it by 2. So I get 1.91 moles of oxygen gas. So we had to use half of the amount of moles of carbon monoxide. Okay, I had to use that half of that molar amount of oxygen to react with all of that carbon monoxide to create the carbon dioxide. Okay, so these are now just equivalencies. If we look at the balanced equation, I need double the amount of carbon monoxide compared to oxygen to create carbon dioxide. Okay, so these stoichiometric conversion factors are what we call those conversion factors to convert from one mole to another. So it is a ratio of the coefficients from the balanced equations. So again, this is why we need to master balancing chemical equations, because if we can't balance the equation, we can't use the right ratio for doing these types of problems. This is oftentimes referred to as a mole-to-mole ratio. If we are converting from one chemical species to another chemical species, we must use a mole-to-mole ratio. There is no other way to convert from between two different chemical species. Okay, there is no equivalency to them besides the mole-to-mole ratio, which we get from a balanced chemical equation. Okay, so if you ever see us converting from one chemical species to another, it means we have to use a mole-to-mole ratio. We can follow a simple pathway to complete these types of problems. So we have our grams of substance A that we can convert to moles of A, which we know how to do. We've done that before. We just use our molar mass. In order to convert from moles of A to moles of B, that is when we have to use our stoichiometric conversion factor, or our mole-to-mole ratio. We sometimes see this as the heart of the problem, because there's no other way to go from one side to the other without going through the heart. So once we have moles of B, we can then convert it to grams of B using our molar mass. So what we're doing here is we're saying, okay, we've done this half of the math, and we've also done this half of the math before, right? Those are the same steps. We're now connecting both sides using our mole-to-mole ratios. So we've always focused on one substance at a time, one atom, one molecule, drawing its structure, knowing its molar mass. But now we can convert between two different types of molecules, two different compounds, because now we have their balanced equations, and now we can convert between them using those mole-to-mole ratios. Okay, so we're taking what we've learned, which is each half of this equation, okay, and we're now connecting it using our mole-to-mole ratios from our balanced equation. We're taking it one step further. So, our balanced chemical equations are used to predict how much product will form from a given amount of reactant, as well as how much reactant is needed to produce a given amount of product. That can go both ways. So, in the formation of water, we start with 0.500 moles of O2. What mass of water is formed? So, before we can solve this problem, we need a balanced chemical equation. So the formation of water, so that would be a combination reaction. Water is formed from H2 and O2, and we get H2O. Okay, we've balanced this in the past. We just need a 2 here and a 2 there. That balances our equation. We've looked at that in our simulation, and we've also done a similar problem in a previous example. So that's how we balance that equation. So now that I have the balanced equation, I'm going to start my calculation with my moles of oxygen gas. So I start with 0.500 moles of O2. So I'm starting from here. I want to know the mass of water formed. So I want to get to here. So O2 is my substance A, and water is my substance B. So my first step is to use my stoichiometric conversion factor. Okay, that's step 1 to go along the way. So my moles of oxygen, I want to convert to moles of water. So I'm converting from moles of A to moles of B. So I'm going to use my equivalency of 1 mole of O2 is equal to 2 moles of H2O. Okay, and this shows us here that the equivalency, the coefficient of B should be on top and the coefficient of A should be on the bottom so that they cancel. So we see that moles of O2 cancel, and I'm left with moles of H2O. So that brings me, I'm now here. So I have moles of water. Let's see, 0.5 times 2, that's 1.00 moles of H2O. I now want to use my molar mass of substance B, which is the molar mass of water, to convert from moles to grams of water. Now, we've done that before. I've given you mole values and asked you to convert them to grams. We've done that in multiple chapters so far. So we are fully capable of now doing that portion of the problem. So we need to find our molar mass of water. So our molar mass of water is going to be 16 plus 1.01 times 2, 18.02. Here's my problem. There it is. So I'm going to put 18.02 grams of water on top and 1 mole of water on the bottom. If you're confused by this portion of the math, why am I putting moles on top and grams on bottom? How did I get molar mass? Please remember to review your notes from previous chapters where we've talked about this, okay? So how to find molar mass, how to utilize it, how to convert between moles and grams using molar mass. We've done that multiple times now. Okay, so I'm taking 1 times 18.02, so that gives me 18.02 grams of H2O. Let's get sig figs in there. That gives me 18.0 grams of H2O. And that's my final answer. So we've done this. This is done in the past. We've covered that. Our new step was just our mole-to-mole ratio, which comes from our balanced equation. Okay, let's look at another problem. How many moles of CaOH2 calcium hydroxide are required to react with 1.36 moles of H3PO4 to produce calcium phosphate, according to the following equation? So I give you the balanced equation. We now want to convert from moles of H3PO4 to moles of CaOH2. You'll notice in this problem that the Ca3PO42 is kind of there as a confusion point. So you just got to make sure you're reading these problems correctly so that you know what you're converting to. So the question is asking how many moles of CaOH2. Okay, so that's automatically where my answer needs to be. I'm going to want to find moles of CaOH2. And I'm given moles of H3PO4. So we're given moles of A, and we want to get to moles of B. So all we have to do is set up our stoichiometric conversion factor, or our mole-to-mole ratio, in order to solve this problem. So we're going to start with 1.36 moles of H3PO4. I'm then going to set up my conversion factor to cancel out moles of H3PO4, so I'm left with moles of CaOH2. So my coefficient in front of H3PO4 is 2, so I'm going to do 2 moles of H3PO4. And the coefficient out in front of my CaOH2 is 3. So we have 3 moles of CaOH2. So we're going to take 1.36 and we're going to multiply it by 3 divided by 2. And we get 2.04 moles of CaOH2. So in order to react with all of my 1.36 moles of H3PO4, I need to use 2.04 moles of CaOH2 to create Ca3PO4, calcium phosphate. And that's what the question was asking. Okay, so let's take this stepwise now. One thing I want to point out here is that we need to label everything. because now we're dealing with things that have same units, moles and moles, but the values are going to change depending on what the compound is. So here I'm making sure that I put 2 moles of H3PO4 and 3 moles of CaOH2, just so that I can see how specific units are canceling out, because moles and moles, if I just left this as moles and moles, I would not be positive that I'm canceling the right numbers. What if I accidentally swapped those numbers? Okay, so by adding these labels, it's another way to check that we've done the math correctly. Okay, so label everything. Okay, so let's take this stepwise now. What is the stoichiometric conversion factor needed to convert from moles of CO2 to moles of NO2 given the following chemical equation? So think of this as substance A is O2 and substance B is NO2. How would you set up the stoichiometric conversion factor to convert from moles of O2 to moles of NO2? You have some options here, so look at those options and pick which answer you think is correct. Okay, so if I started with moles of O2, let's say I have some number here, and I wanted to set up a conversion factor that would cancel out moles of O2 and I'm left with moles of NO2, well, I would want to have moles of O2 on the bottom and moles of NO2 on the top, so that we can see that moles of O2 cancel and we're left with moles of NO2. We now have to figure out the numbers that are going to go in front of that. We get those values from our balanced equation. So we look to O2 and we see what its coefficient is. The number out in front is 7, so we put that there. And then we look to NO2, and the number out in front of NO2 is 4. So that is the valid ratio to convert from moles of O2 to moles of NO2. So that would be letter E. So let's use that conversion factor now. So we said 4 moles of NO2 and 7 moles of O2. Let's use that conversion factor now to determine how many grams of NO2 gas can be produced from 45.5 grams of O2 gas in the following chemical equation. So it's the same equation that we had before, now I'm just giving you numbers. We're starting from grams of A and we want to get to grams of B. We know what our stoichiometric factor is, that's the heart of the equation. Okay, so what we have to do is convert from grams of A to moles of A using our molar mass. Use the stoichiometric factor that we determined on the previous example to convert from moles of A to moles of B. And once we have moles of B, use its molar mass to convert to grams. So take a second and try that yourself. Okay, So we're starting this problem with 45.5 grams of O2 gas. And our first step is to convert it to moles using the molar mass of oxygen. Now we want to use the molar mass of O2, okay, so we want to use 32 grams, is in 1 mole. So 45.5 divided by 32 gives us 1.42185 moles of O2. We next want to use our stoichiometric conversion factor to convert from moles of O2 to moles of NO2. And we're going to use our 4/7 ratio from our previous example. So it's going to be 4 moles of NO2 for every 7 moles of O2. So we're going to take that 1.4, we're going to multiply it by that ratio of 4/7. And that's going to give us, I'm going to write it down one line, 0.8125 moles of NO2. So I have successfully converted to moles of substance B, moles of NO2. And the question wants me to get the mass, so I simply have to use the molar mass of NO2 to convert from moles to grams. So we need to find the molar mass of NO2. So we're going to use our periodic tables to find the molar masses. 14.01 for nitrogen, 16 times 2 is 32 for oxygen, and we get 46.01 grams for every 1 mole of NO2. So we're going to take 46.01, multiply it by 0.8125, and we get 37.383 grams of NO2. Our initial number had 3 significant figures, so this should round to 37.4 grams of NO2, which we see as answer A. I'll zoom out so you can have a full look at that. So I just followed my little track here in order to get that mass. I have a molar roadmap here, and that's what this is called, the molar roadmap. And you have this in your lecture notes, okay? And I say that the figure on the bottom of the previous page is referred to as the molar roadmap. You can use this roadmap to go between any 2 boxes. You simply start at one box. This is your known information given in the problem. You then follow the arrows to navigate to the variable the problem is asking for. Each arrow tells you the value you need to use to convert between the values. So the example I give, I believe it's down here. For example, if we were given number of particles or molecules of B and wanted to calculate the mass of A, we would first convert the particles of to moles of B. So let's see, we're starting at particles of B, so we're starting here, and we want to get to mass of A. So we follow the arrows in order to do that. So the first thing we have to do is convert from number of particles to moles using Avogadro's number. Once we have moles of B, we want to convert to moles of A using our stoichiometric factor, or our mole-to-mole ratio. Once I have moles of A, I can then find the mass of A by using the molar mass. Okay, so it's just a roadmap. You know where you start and you know where you need to finish, and you follow the arrows along the way. Okay? And then you do whatever conversion factor it tells you to do to go from one box to the other. So you have this handy in your lecture notes. It's also provided as a test resource for you to review and utilize in your homeworks and in your exams, so that you can easily figure out what you need to do to convert and find whatever value you need. I will note that we have not gotten to this point yet. We have not done that yet. We will get to that in chapter 9, okay? But it is useful for there as well, but for right now we will ignore it. I would also like to point out that if you look at just one half of this, this is what we've used to convert between mass, moles, and particles in the past, whenever we've done those conversions. Okay, we've done that in 2 chapters now. So I'm just combining those 2 conversion charts, okay, 2 of the same conversion charts, now just using our stoichiometric factor again to show that they connect. Okay, so again, this is the heart of the problem. Okay, so let's put this all together. So we're going to use our little molar roadmap there that we have. Consider the reaction of octane. Using the balanced equation, answer the following questions. What mass of oxygen gas is consumed if 703 grams of octane is combusted? And how many molecules of oxygen are consumed? So we're starting with a mass of octane. So let's go to our chart here. Let's erase some of these things. We're starting with a mass of A. So here's where we're starting. And we want to get to the mass of B. So that's our ending right here, mass of B. So to do that, this is our normal loop. We're going to use molar mass to go to moles of A, mole to mole ratio to get to moles of B, molar mass again to get to mass of B. The second problem is then asking us to find the number of particles. So we can either start from the mass of B and end at number of particles and do molar mass to moles and moles to Avogadro's number, or we could start at mass of A and instead of using, once we get to moles of B, go to Avogadro, use Avogadro's number. We can do it multiple different ways because our molar roadmap allows us to do that. So let's look at that problem. I have some extra room here. So what mass of oxygen is consumed if 703 grams of octane is combusted? So our molar roadmap tells us we have to go from grams to moles of A. Then we have to go to moles of B. And then from moles of B to grams of B. So what I want you to do is pause the video and solve that first part of the problem on your own. The first thing we have to do is find the molar mass of octane, because that's the only way we're going to convert from grams to moles of octane. So we use our periodic table to do our molar masses. Let's see, we have 18 hydrogens. So we have a molar mass of 114.26. So we start with 703 grams of octane. We then use our molar mass to convert from grams to moles. So we take 703, not 7.03, 703 divided by our answer, and we get 6.1526 moles of octane. So we've gone from grams to moles, so we're here. We now want to go from moles of A to moles of B, so we're going to use our balanced equation. We're going from octane to oxygen. So we want to put moles of octane on the bottom and moles of oxygen on the top. Our stoichiometric factor for octane is 2, and for oxygen is 25. So we're going to take that 6.15, we're going to multiply it by that ratio, 25 over 2, and we get 76.9079, oops, not grams, moles of O2. So now that we're at moles of B, we want to get to grams of B, so we're going to convert from moles to grams using the molar mass of oxygen, which is 32. Okay, moles will cancel. I'm going to take that and multiply it by 32. And we get a value out of 2461.0537 grams of O2. Our original number only has 3 significant figures, so we want to write this as 2.46 times 10 to the 3 grams of O2. Okay, so that answers our first problem. Now for our second problem, we want to know how many molecules of oxygen are consumed. Well, I know from my molar roadmap that if I know my moles of B, I can convert to number of particles using Avogadro's number. Now I wrote down before moles of B, moles of oxygen was 76.907, okay? So I can use Avogadro's number to now go from moles to molecules. So we take 76.9079 moles of O2, and we are going to multiply it by Avogadro's number, because Avogadro's number is 6.022 times 10 to the 23rd molecules in 1 mole. So that would allow us to cancel out our units of moles and be left with units of molecules. So let's take 76.9079 and multiply that by 6.022 times 10 to the 23, and that gets us 4.63139 times 10 to the 25th molecules. And with sig figs, we're going to do 3 again, so we have 4.63 times 10 to the 25 molecules of O2. Okay, now you could have started the whole problem again with 703 grams of octane and done your conversions and then gotten here again and then converted. That's totally fine. You could have started from your mass of oxygen and converted it back to moles and then to Avogadro's number. You could have done it that way as well. The whole thing with the molar roadmap is you still get to that destination regardless of the path that you take, because there can be multiple paths on how to solve some of these problems. Okay, so you can try it both ways and prove it to yourself if you'd like. Okay, let's continue to practice. So, given the following reaction below, determine the moles of molecular chlorine used in the reaction. So the first thing we have to do is balance the reaction. And then, if in one reaction 0.507 moles of SiCl4 was produced, how many moles of chlorine did we use? Okay, so let's balance this equation first. Let's set up our chart. We only have 2 Si and Cl. I have 1 Si, 2 Cls, 1 Si, 4 Cls. So I have unbalanced chlorines. I just need to add a 2 here to balance it out to 4, and that's all we needed. So now we're just going from moles to moles, so we're just using a simple mole to mole ratio to do that. So we're starting with 0.507 moles of SiCl4. Okay, so what I want you to do is pause that video, and I want you to set up the equivalency to cancel out moles of SiCl4 and be left with moles of Cl2, and solve the remainder of the problem. Okay, so we want to put moles of SiCl4 on the bottom and moles of Cl2 on the top, so that moles cancel. We then just have to look at our balanced equation for our numbers. SiCl4 has a coefficient of 1 and Cl2 has a coefficient of 2. So we're just going to take that 0.507 and multiply it by 2. And we get 1.014 moles of Cl2. With sig figs, this would be 1.01 moles of Cl2. Okay. Let's try the next one. For many years, the extraction of gold from other materials involved the use of potassium cyanide. That's KCN. What is the minimum mass of KCN needed to extract 29.0 grams of gold? Remember, gold is AU. So we're starting at grams of A. We want to get to grams of B. So what I want you to do is attempt this problem independently and then come back to the video to check your work. We're starting this problem off by taking our grams of gold and converting it to moles using the molar mass of gold. We find that directly on the periodic table. So we're going to start with 29 grams of AU, and the molar mass of gold is 196.97 grams. So that gives us 29.0 divided by 196.97. We get 0.14723 moles of gold. We now want to use our stoichiometric factor to convert between moles of gold and moles of KCN, potassium cyanide. So we're going to use moles of AU on the bottom so that it cancels, and moles of KCN on the top so that we're left with that unit. Okay, so we'll see that moles of AU cancel. Our coefficient out in front of gold is 4, so we're going to put 4 there. And our coefficient out in front of KCN is 8, so we're going to put 8 there. So we'll take that 0.14, we'll multiply it by that ratio of 8 over 4, and we get that the moles of KCN is 0.29446 moles of KCN. Our last step is to then use the molar mass of KCN to convert it to grams. I'm just going to move down one line. 0.29446 moles KCN. The molar mass of KCN is 65.12 grams. Just check your periodic table to make sure you get that mass. And that's for every 1 mole of KCN. So we take that value, multiply it by 65.12, and we get 19.1753 grams of KCN. And with sig figs, let's see, we had 3 in our starting, so we want to have 19.2 grams of KCN. Okay. This next problem is a little bit of a tricky one because we're now asked to find the volume that can be produced from this reaction. So, part of winemaking is fermentation, a complex chemical process that converts glucose to ethanol and carbon dioxide. What is the maximum quantity of ethanol in grams and in liters that can be produced from 500.4 grams of glucose? So, what we're going to want to do for this problem is we're going to start at grams of A, which is glucose, and end at grams of B, or ethanol. Okay, we're going to do it just like we did in our previous example. Except now that's going to take care of the grams portion. We're then going to use that grams of B and the density of ethanol to convert between grams and volume. Now we did that way back in chapter 1, so this may be a little bit of a refresher, okay, but remember density is just a unit of grams per milliliter, so if we know the grams, we can use the density to find the milliliters. Okay, so let's start this problem. We're going to start just like we did before. We have 500.4 grams of glucose, which I'm just going to call glue. And we're going to convert it to moles using its molar mass. So 1 mole of glucose has a molar mass of 180.18 grams. You can find that from the periodic table. Add up all those carbons, hydrogens, and oxygens. That's going to get us our moles of glucose. So that is 500.4 divided by 180.18. And you get 2.77722. So that's moles of glucose. We'll then use our stoichiometric conversion factor to go from moles of glucose to moles of ethanol. So we'll put moles of glucose on the bottom and moles of ethanol. There we go, ETOH, ethanol, on the top. Okay, that'll allow us to cancel out moles of glucose. Glucose has a coefficient of 1. Ethanol has a coefficient of 2. So we're going to take that number and multiply it by 2. So we get moles of ethanol to be 5.55444 moles of ethanol. I think we have enough room. So once we have moles of ethanol, we can use its molar mass to convert. So we have 1 mole of ethanol has a molar mass of 46.08 grams. So we'll multiply that by 46.08. And we get 255.948 grams of ethanol. With sig figs, we have 4, so we have 255.9 grams of ethanol. And that's our first answer. Now the second part of this problem asks us to do the volume in liters. So we have grams of ethanol. We can use the density of ethanol to solve for the volume. So we can say that the density is equal to the mass over the volume. So I know my density is 0.789. My mass that I'm looking for is 255.9 grams, and I want to find X milliliters. So we take 255.9 and we divide it by 0.789. I'm just rearranging my equation using basic algebra. So we get X milliliters to be 324.334 milliliters, and the problem specified that it wants it in liters. So we have to remember that in 1 liter there's 1,000 milliliters, so we're going to divide that value by 1,000, and we get 0.3243 liters with sig figs. So that's our final answer. Okay, I want you to try this next problem on your own. Ammonia is a colorless gas with a pungent characteristic odor. It is prepared by the reaction between hydrogen and nitrogen. In a particular reaction, 6 moles of NH3 were produced. How many moles of H2 and how many moles of N2 were consumed to produce this amount of NH3? So we're just using simple mole-to-mole ratios to solve this problem. So pause the video and do that on your own. Okay, so we have to do this conversion twice. So we're going to start with 6.0 moles of NH3, and let's convert to H2 first. So we want to put moles of NH3 on the bottom and moles of H2 on the top. So we look at our coefficients. NH3 has a coefficient of 2. H2 has a coefficient of 3, so we just take 6 and we multiply it by that ratio of 3/2. Because that's canceling out moles of NH3, we're left with moles of H2, so we get a value of 9.0 moles of H2. The next thing we want to do is, again, start with 6.0 moles of NH3. We can use our coefficients again. We know that's going to be 2 moles of NH3 to cancel out. We now have to substitute our H2 for an N2. Our coefficient in front of N is 1. So 6 divided by 2 is, let's show how these cancel. 3.0 moles of N2. Perfect. Okay, on to our last problem of this lesson. Nitrous oxide is also called laughing gas. It can be prepared by the thermal decomposition of ammonium nitrate. The other product is H2O. Write a balanced equation for this reaction and determine how many grams of N2O are formed if 0.46 moles of ammonium nitrate is used in the reaction. So, A, we want to write our balanced equation. Well, it's given to us that we start with NH4NO3, ammonium nitrate. We've done a similar problem with ammonium nitrite previously. And we say that it decomposes into N2O, nitrous oxide, laughing gas, and H2O. So we can balance this now. Again, just like our previous example where we had ammonium nitrate is again made up of 2 polyatomic ions. Because those polyatomic ions are decomposing into 2 different products, we're not going to keep them together. So we're going to have nitrogen, hydrogen, and oxygen as individual elements in our balancing. So nitrogen, we have 2 on either side. Hydrogen, we have 4 on the reactants and 2 on the products. And oxygen, we have 3 on the reactants and 2 on the product. So let's balance our hydrogen first. We have 4 on reactants and 2 on products, so I'm going to put a 2 out in front of the water. That 2 is going to cause that hydrogen to go from 2 to 4. And the 2 is also going to cause the oxygen to double. So now I have 2 oxygens plus 1, which balances it out to 3. So we now have a balanced equation amongst all of it by just adding that 1 coefficient. Okay. So, the second part of the question says, how many grams of N2O are formed if 0.46 moles of ammonium nitrate is used in the reaction? So we're starting with 0.46 moles of NH4NO3, and we want to somehow get to grams of N2O. Well, I have moles of one compound and I want to get to another. I have to go through a mole-to-mole ratio. So 1 mole of ammonium nitrate is equal to 1 mole of N2O, which gives us 0.46 moles of N2O. Now that we have moles of N2O, we just have to convert it to grams using its molar mass. So 0.46 moles of N2O, well, 1 mole of N2O has a molar mass of 44.02 grams. So we take that 0.46 and we multiply it by 44.02. and we get 20.2492 grams of N2O. I only have 2 sig figs in this problem, so we would write this as either 20 with a decimal at the end grams of N2O, or you could write this as 2.0 times 10 to the 1 grams of N2O. Either is acceptable. Okay, so that's our last practice problem of this lesson. I strongly encourage you to continue practicing with that balancing simulation, as well as go into your ALEKS homework and practice using balanced equations in these types of problems where we have to convert between 2 chemical species using our mole-to-mole ratios.